So I've written the problem setup, and we have the matrix A with our data points for x and our vector y with y. And I've taken the transpose and I've written it on the left because we'll be applying matrix multiplication to this side to solve for A transpose A. And then we'll also matrix multiply A transpose with y. So if we multiply these two matrices, it's the first row here times the first, take the dot product with this column, and that's x1 squared plus x2 squared plus xd squared. So the first top left entry is the sum of the squares of these entries from 1 to d. And the second entry on the top is the first row times the second column of A, and that's x1 times 1 plus x2 times 1. In other words, we're just summing up all of the different x values. And on the bottom left, it's the second row here with the first column. That's the same as it was in the top right. And then the last entry on the bottom right is the second row with the second column. And that's 1 times 1 plus 1 times 1 plus 1 times 1, d times, which is just d itself. So this is A transpose A. And A transpose Y equals, first of all, notice that it's just a 2 by 2 matrix. So we're going to be solving a rather simple system. It's just a 2 by 2. So A transpose Y is now take the values of x, multiply them with the values of y. It's sum I equals 1 to d, xi with yi this time. And then it's the second row with this, and that's just the sum of the y's. And it's our vector with two components here. And we want to solve this system. Now, it's only a 2 by 2. So on the one hand, we could probably set this up as a row reduction, an augmented matrix problem, row reduce and isolate whatever we need to so that we can solve for this vector c. On the other hand, it's only a 2 by 2 matrix, and row reduction might be a little bit complicated. For instance, we might want to maybe divide this entry by the sum of the squares of all of the entries, but maybe that's a problem if every single one of these is 0. It's a little bit tricky. So it's very convenient to first of all find out when this matrix is invertible. And if this matrix is invertible, we can multiply both sides by the inverse. So if A transpose A inverse exists, and we'll figure out what that means. We'll compute the determinant of this to determine when this inverse actually exists. Then we can solve this system pretty easily. And it's c, which is, again, remember, our vector of unknown coefficients m and b. Then this equals A transpose A inverse times this vector right here, A transpose y, which we've already computed. So, in terms of the setup, it's relatively straightforward. Maybe calculating this actual inverse might be a little bit of a challenge because of the arbitrariness, the generality that we're doing this in. So first, let's compute the determinant of this matrix. And that's just this times this minus this times this. Now, because we're multiplying these two sums, we really have to be careful about the indices. Remember, this is a sum of stuff multiplied by a sum of stuff. So we can't just say that this is sum xi squared. It's actually, there's a lot of foiling going on. And this is given by d, the sum of the squares. That's from the first term, this times this, minus this times this. And in order to make that calculation a little bit more straightforward, I'll rewrite one of the indices as a j instead of an I so that we don't get confused. So this is xi times xj. And each of these sums, there's actually two sums here, one for the index I and one for the index j, and they both go from 1 to d. So this is the determinant. And I won't do the rest of this calculation out, but this, I'll make a claim, and you should check this, that this equals 0 if and only if xi equals xj for all I and j. So the only time that this determinant vanishes if all of the xi data points happen to be equal to each other. Now, it takes a little bit of time to actually show that, but you can do it. And this is the only instance when this matrix is not invertible. And if you're thinking about data, this basically would mean that all of your data points lie along a vertical line. And then it makes sense that you can't find a function of the form y equals mx plus b to fit this, because the only line that'll work is a vertical line. And in that case, the slope is infinite, so you won't find a solution. So it makes a lot of sense why this is the only case where that happens. Otherwise, if you have even a single point that's off of this line, you will be able to find some curve that best approximates this data. Although you would think that maybe if all of these points lie here and there's a data point way out here, then maybe this data point is, there's something wrong with it, or more investigation is needed. Such a point in this situation would be called an outlier. And I may discuss about this at some point, but that's not the focus of this specific video right now. So that's the claim. So this determinant vanishes if and only if all of these data points are equal. So let's assume that this does not happen. Assume there exists an I and a j that's not equal, an I and a j which they are not equal, and such that xi is different from xj. So we just need to assume that we have at least two data points that do not lie on, that are not the same. When we make this assumption, we can compute this inverse. And this is easy because it's just 2 by 2. We maybe remember this formula. We just divide by the determinant. We swap these two entries, and we negate these. So this is just 1 over this determinant. And I don't want to keep writing it, so let me just write determinant of A transpose A. And just remember that it equals this. And then we swap these entries. So this is D. And here we have sum. And there's lots of indices now, and I don't want to conflate any of these indices with each other. So I'm now going to call these K or something. So this is K equals 1 to D. And this is x k squared. And here we have minus sum xk. Oops, k goes from 1 to D. And this is minus k from 1 to D. And this here is the inverse of our matrix. And then what we have to do is we have to take this complicated expression and multiply it by this vector. And once we do that, we'll find out what the values of m and b are. So we'll need, again, a little bit more board space to do that.